Well, welcome back, and hopefully you've had a bit of practice with oxidation states and oxidation numbers. And now we're going to take our idea of simple redox equations and redox reactions and start applying them to some organic compounds and some other slightly trickier situations. So going through what we want to be able to do after we've watched this video, we need to be able to understand that redox reactions for covalent compounds require a different process for balancing compared to pure ionic substances. Understand the rules for balancing complex redox reactions. Apply the rules in order to be able to balance redox equations for common oxidizing agents such as permanganate or dichromate. And then apply these rules to balance redox equations for the oxidation of alcohols in acidic conditions or other organic compounds. So basically being able to pull out those half equations and overall equations for things where the electron transfer isn't so straightforward. So if we think about what we've been doing already in terms of simple redox equations, and when I talk about simple redox equations, I'm talking about things like the demonstration that we looked at where we talked about copper solid plus silver nitrate solution, this displacement reaction going to copper 2 plus plus Ag solid. Okay, that we looked at previously. So if we keep to the ionic equation, look at it this way, we'll need two, we'll just leave it like this. So being able to pull out the half equations, we need to pull out our redox pairs, so our copper. So Cu solid going to Cu2 plus 2 electrons. Or in the case of our silver, we can see that it's being reduced going from Ag plus to Ag solid, and we will need 1 electron over here. And then the idea that we can then multiply this by 2 if we wanted to write the overall equation, and we would then end up with Cu solid plus 2 Ag plus aqueous, running out of room here, plus 2 electrons is going to go to 2 Ag solid plus Cu2 plus aqueous plus 2 electrons, and then I can cross out my electrons. And we have the overall balanced equation. Okay, so in this case, again, if we review our oxidation numbers, we can see copper is solid and in elemental form here, so it would be 0, plus 2 for our copper 2 plus because it's always the same as the ion. Or with silver, Ag plus going to Ag solid, we have that plus 1 going to 0. So we can see here that our oxidation state increases from 0 to plus 2. So it is oxidation that is occurring. Or in the case of the silver, we go from plus 1 to 0, so it's reduction that's occurring. So essentially what we've done is followed these steps, making sure that our electrons balance at each point so that we are not having just random electrons hanging around. And then when we pull them back in for this final step, we can add in back in our spectator ion. So we would add in our nitrate again to give the full balanced equation if the question asks for it. So this is just another example. In this case, this is a copper oxide and zinc reaction. You may actually remember way back when in the beginning of our studies in chemistry, we did that really great copper prac where we started with copper metal, took it through a whole series of reactions and then displaced the copper metal again at the end. And this is a similar process to this. So we have copper oxide reacting with zinc, forming zinc oxide and copper solid. So if we look at the oxidation numbers of these, here we would see oxygen is always minus 2, so copper would be plus 2 in this case, oxygen is minus 2, zinc would be 0 because it's a solid, zinc in zinc oxide would be plus 2 because oxygen is minus 2, and this would be 0. So we can see for our zinc it goes from 0 to plus 2, so this is oxidation, the copper from +2 to 0. So we have reduction, and we can confirm that again by the positions of our electrons. Okay, so because zinc is the electron donor, it allows copper oxide to be reduced. So zinc is the reducing agent. The reducing agent is always oxidized. Copper is the electron acceptor, which allows zinc to be oxidized. So copper is our oxidizing agent or oxidant, and is reduced in the process because it is accepting those electrons. So this is just another one showing another example of an ionic equation. I'm not going to go through it in detail because I think we're pretty good with this. All we are looking at here is realizing that chlorine, the chloride in here, is just a spectator ion. What's really happening when we have that acid with metal reaction that we've talked about previously is that it's actually the hydrogen ions and the magnesium, not the spectator ions, that are reacting. So that metal plus acid reaction that we've become familiar with is actually a redox reaction, which is why we don't classify it as a Bronsted-Lowry acid base. Okay, things get a little bit more complex when we have covalent compounds involved and we can't see that electron transfer quite so clearly. I'm going to go through the steps, but really the easiest way to learn how to do that is just do a couple and look at the examples. So again, we do exactly the same thing. We find our redox pairs and we write our half equations for the oxidation or reduction showing the conjugate redox pairs. So that's just finding our redox pairs, so like copper solid and copper 2+, or our alcohol, propanol and propanoic acid. We balance the half equations for all elements except hydrogen and oxygen. So chromium or any of our metal ions we balance, or anything else like that, but we leave hydrogen and oxygen alone. Okay, and just a point, we have to do these steps in order. Then, once we've done everything except hydrogen and oxygen, we balance for oxygen by adding water. So if I have 5 oxygens on one side of the equation, I'll add 5 water molecules to the other side of the equation. I can only add water. Once I've balanced all my oxygens with water, I add H+ ions to the side that needs them. So I balance my hydrogens by adding H+ to the side that needs more hydrogen. Obviously, if I'm adding H+, I'm going to mess with my charge. I'm going to get a lot of H+ charges on one side that aren't on the other. So what I do then is I balance up that charge by adding electrons. And because electrons are negative, I can't take away positive charge. What I can do is add in negative charge. So we usually add the electrons to the more positive side of the half equation. Then we multiply each half equation by factors that will give us the same number of electrons, and then add them together the same way we have before, make sure all our states are in and everything's okay. That's a lot of steps. Let's have a look at it. So if we look at dichromate, so our Cr2O72-, you'll remember that this was one of our strong oxidizing agents we talked about for organic reactions, and we said that it always had to be in acidified conditions. Now, if you think back to the rule that says we have to have H+ to balance hydrogen, that's why it has to be in acidified conditions. So we have a source of H+ to allow this redox reaction to go. So if we think about this, first of all, Cr2O72-, we need to know what it will turn into. This is something that you should put on a flashcard or remember. When dichromate is reduced, it turns into chromium 3+. Because I have 2 of them in dichromate, I will need to use a coefficient in front of the chromiums when I balance out my chromiums. So step 1, balance all atoms except oxygen and hydrogen. So in this case, I have 2 chromiums on the left-hand side. It's going to go to 2 chromium 3+ on the right-hand side. Okay, step 1 done. Step 2 was balance oxygens by adding water. Now, I have 7 oxygens on the left-hand side. I will need to add 7 water molecules on the right-hand side. Done. That's step 2. Step 3 was to balance any hydrogens by adding H+. And because we've added these 7 water molecules, I now have a lot of extra hydrogens on the right-hand side. So in fact, I have 14 hydrogens on the right-hand side. So I have to add 14H plus over on the left-hand side. Now it's balancing charge. Now this is where we need to pay careful attention. So if I have a look here, if I want to balance this charge, I have two lots of 3 plus. So on the right-hand side, I am at +6. On the left-hand side, I have 14, so plus 14 here, but I have -2 from the dichromate. So overall, that means my charge on the left-hand side is +12. Yeah, I need to make these two numbers balanced, +12 and +6. The only way I can get from 12 to 6 is by adding electrons. And I need to add 6 lots of negative in order to get that right. So I'm going to go from 12 to 6 by minusing 6, which is the same as adding 6 electrons. So now on this side, my charge is +6, and on this side, my charge is +6. And when we talk about balancing charge for the half reaction, we are not talking about making it 0. We're making it equal on both sides. Okay? Because then when we would put this in, this is our reduction equation, as we can see, because our electrons are on the left-hand side. When we have the corresponding oxidation equation, we'd add them together and those electrons will move. Okay, write down your rules, pause the video, and have a go at doing the reduction reaction for permanganate. Okay, essentially, complex redox equations, we need to use them whenever our reactant is going to have oxygen in it, because we've got to get that oxygen in somehow, and we do it by following it this way. So pause. It's going to go from MnO4 minus to Mn2 plus. Have a go, and then come back and check out the solution. So welcome back. Hopefully you've managed to do it. I'm halfway through mine here, and I thought I'd pause at this point just to make sure. So first of all, I've balanced my MnO4 minus to Mn2 plus. So I've got a manganese on the left and a manganese on the right. After that, I had 4 oxygens, so I've added 4 H2O. Now, because I have 4 H2O, I have 8 hydrogens, so I added 8 H+. So I'm up to that bit about balancing charge. So I need to look at my charge. On this side, I have 8 H+ and -1, so that's going to be +7 on this side. And on this side, I have +2. Okay, so to get from 7 to 2, I'm going to add in 5 electrons. Okay, so you will get so much practice with these dichromate and permanganate equations that you'll probably memorize them off by heart, but the process always works irrespective of that. And then I can throw in my state, so it would be aqueous, 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 and liquid here. Okay, so this would be the half equation for the reduction of permanganate. Let's look at how this works rather than just a half equation. Let's look at the whole process. So this question is asking us to work out the overall redox equation for the oxidation of ethanol to ethanoic acid using acidified potassium permanganate, and it's told us that it reacts to form Mn2+. Okay, so we are looking at ethanol. So CH3CH2OH. Okay, so that's going to be a liquid, plus MnO4 minus, aqueous, reacting to form. Now the oxidation of ethanol is going to give me ethanoic acid, so CH3COOH, liquid, plus Mn2 plus, aqueous. Okay, this isn't balanced. It's not going to be balanced. I need to deal with these oxygens in the permanganate, but it does allow me to see my redox pairs. So first things first, let's pull out our two half equations. So CH3COOH, let's get rid of that acid on this side. We want the alcohol, and it's not. Okay, going to cross that out. It's going to get a bit messy. So CH3CH2OH, liquid, is going to go to our alcohol. our carboxylic acid. Okay, so because I have oxygen in my reactant, I'm going to have to use our rules that we established before. Okay, so in this case, CH3CH2OH, I have one oxygen on this side and I have two oxygens on this side. So now my water is going to have to come over onto the left-hand side. Okay, now I've got to check my hydrogens. So I've got 1, 2, 3, 4 on the right-hand side. On the left-hand side, though, I've got 3, 4, 5. Don't forget this guy, 6, and then 7, 8. So I have 8 on this side, 4 on this side. So I'm going to have to add 4H plus over onto this side. Okay, now ethanol is neutral, water is neutral, ethanoic acid is neutral. So my only charge is coming from 4H plus. So I need to make, has a 0 charge on the left-hand side. I'm going to make this 0 on the right-hand side. So I'm going to add 4 electrons onto this side. Okay, I've produced electrons, and I know that alcohol going to carboxylic acid is oxidation. So this is my oxidation reaction. All makes sense. And then that means I'm left with MnO4 minus, which is the one we just did, going to Mn2 plus 4 H2O over here with my 8H plus. So 2 plus here, 7 plus here, so 5 electrons. Now I've got a bit of a mess. I've got 4 electrons here. I've got 5 electrons there. I need to get them to a common factor. So if I multiply this one by 5 and this one by 4, I'll end up with 20 electrons in each one. So let's have a look. So I will end up with 5, 5, 5, 20, and 20. And then I will end up with 4, 4 8s are 32. Okay, 20, 4, 16. Okay, so now this is going to get, let's see if I can go with a different color. Let's go with green. Okay, so now what we've got is I need to find the things that are on both sides of the equation. So I've got this water here and this water here. So because I have 5 here, I can lose those, and that will leave me with 11 waters over here. Okay, and then I have 20 H plus over here and 32 over here, so that will leave me with 12. I have 20 electrons and 20 electrons, so that leaves me with none, which is fantastic. So now I need to work out the rest of my overall equation. So I have 5 lots of ethanol, so 5 CH3CH2OH liquid plus, so that's that one done, plus 4 lots of MnO4 minus. That's that gone, and that leaves me with 12 H plus. That's that gone, and then I'm going to be left with my 5 lots of ethanoic acid plus my, they're gone, that's gone, my 4Mn2 plus and my 11 waters. Yours will look a bit neater than mine, I hope, because you've got more space to write. So this would be my overall equation here. So the oxidant is what is reduced. So in this case, it will be MnO4 minus. The reductant is what is oxidized. So in this case, it will be the ethanol. And the redox pairs are ethanol and ethanoic acid, permanganate, and manganese 2+. Hopefully that makes a bit more sense. Make sure you read through those dichromate and permanganate examples, and we will definitely do some more of these questions. Practice always makes perfect. So it's a bit of a long one with all the examples, but hopefully you can balance redox equations in acidic conditions. You can figure out whether the rules need to be used or not. So if our compound contains oxygen, you can balance the half equations for dichromate and permanganate because they are really common ones that turn up all the time. And you can now balance an equation for an alcohol through to a carboxylic acid. I challenge you to have a go at seeing how the equations are different when we go from that alcohol to an aldehyde. And we will do more examples in class. So until next time, see you later.